Hello everyone. This lesson we're going to be discussing the conclusion and evaluation sections of lab reports. So, a quick summary of what's been in a lab report so far. This is otherwise known as the exploration section. Usually we start with an aim, and that is usually to calculate a particular number. The true value of this number is quoted. So as a particular example, let's say you were dropping a ball from a range of heights and measuring the time taken to hit the ground. The quantity you could calculate off of that would be the acceleration due to gravity. And the value that you get out of your formula book for that is 9.81 meters per second squared. So that would be the true value. You have a background section. First things first, you explain the physics of the system. So you have an object with a mass, it's going to experience a weight, and therefore it's going to accelerate, and you can write down the relationship between the independent and the dependent variables of your experiment. So for the particular case of the dropping a ball, you have the Suvat equations, and so you can write down S. Oops, why is that not working? S is EUT plus a half AT squared, and you dropped it from rest, so U is 0, and the distance it travels is the drop height h, and the acceleration is g. So you can write down that the drop height is going to be related to the time to hit the ground by h is a half gt squared. You would explain how you linearize your relationship, so how you plot a straight line graph from the expected data. So in this case, what you would do is you would plot h against t squared, and you would sketch what that looks like. So you go h against t squared, and you expect a straight line through the origin with a gradient of a half of g, and you give an expected intercept of 0. So we've discussed the relationship between the independent and dependent variable, that's the equation. How you linearize that, so what you plot against what to get a straight line. How the target number relates to the gradient or intercept. In this case, the gradient is going to be a half of g, and what you expect the other things to be, so we expected the intercept to be 0. This is in effect your hypothesis, what you're going to be testing with the experiment. Then you have a method section which contains an apparatus diagram and a procedure. Then you do the experiment and you do the analysis section. This contains a raw data table, the data you took from the practical. The process data table, if you need one. So for the example of the dropping the ball from a range of given heights, the quantity you need is t squared, not t, because you're going to be plotting h against t squared, so the process data will show t squared and how you calculate the absolute uncertainty in t squared, because you're going to need that for the graph. The graph should have error boxes if you have errors big enough in two directions, or error bars if they're not, and that will give you maximum gradient lines. And we're going to assume that the line of best fit is straight, as you predicted. Then that will allow you to calculate a gradient, an uncertainty on the gradient, the intercept, and the uncertainty on the intercept. So this is where we're up to so far. What's next? The conclusion section is broken down into two parts. The first part is discussing the graph. Firstly, state whether the line of best fit is linear. If the line is straight and the uncertainty on the intercept contains the origin, then we can say the relationship is directly proportional. If you have an unexpected intercept, so you didn't expect one and there is one, this is usually a good indicator of a systematic error. You then discuss what that could be. Does the data follow the relationship you expected? i.e., is the line of best fit the expected shape? Remember that we predicted a shape in the background section. If not, you discuss what's going on. So here we have a linear, a non-linear, and a linear, non-linear, and directly proportional graph. Again, these are terrible examples because they don't have error bars, boxes, and max and min lines. Then the second part of the conclusion section: was your experiment accurate? How do you know if your experiment is accurate? You compare it to the target value. So what you currently have are the gradient and the intercept. So first thing you need to do is calculate the number that was the purpose of the experiment. So in the background section you worked out how the gradient or intercept was related to the quantity you're interested in, so you calculate the quantity. You also need to calculate the uncertainty on your quantity. You usually need some propagation of errors for this. Then the key question: is your experiment accurate? i.e., is the true value contained within the uncertainty of your calculated value, or is it outside? The evaluation section is all about how good the practical was. We now have a way of quantifying how good a measurement is. We have its percentage uncertainty. So this section is about the weaknesses of the method and how to fix them. First thing you do is you list the measured values in the experiment and give a characteristic percentage uncertainty for each. So let's say for the range of heights in the dropping the ball experiment, you only measured each one of those things once, so the uncertainty would be the resolution on your device, so plus or minus a millimeter. And let's say you did it over the range of a couple of meters, that would give you a percentage uncertainty of whatever it was. So characteristic percentage uncertainty, if you've got a number of readings, you can take an average of them. But if any particular points have huge error bars, huge percentage uncertainties, you should discuss why that is. So for instance, if you have taken too small a height for the dropping a ball versus height experiment, then the time it takes to hit the ground will be too small and the percentage uncertainty might be too big. Here's how we know if something is a strength or a weakness. We've given you an artificial cutoff. If we say a value has a percentage uncertainty of less than 5%, it's a strength. That number has been calculated precisely. Otherwise, it's a weakness. And if it's a weakness, give a realistic way to reduce that uncertainty.